Thanks very much to the organisers for inviting me to come along today. This is a building that we work in, and so if it's your first time to visit this Maths Institute, welcome indeed, and I'm glad we arranged some sunny weather while you're here this week. Hasn't been so good. Okay, today what I want to do is I want to talk about some alignments and comparisons between three different approaches to the mathematics of consciousness. They're sort of subjectively selected, so if I'm leaving out your favourite approach, apologies. But the purpose of this is to do what we've always wanted to do in these meetings, is not to have a dialogue of the deaf, where we just split into different camps and all believe we're right, but actually we just compare achievements and non-achievements, we compare outputs, we compare ideas in such a way that everybody benefits. We're encouraging different approaches to make progress, and I believe all three of the processes that I'm talking about today actually could benefit from having a more forceful agenda. And we get that agenda in meetings like this, when we can argue it out in the hall and down the pub. So that's what I'm doing today. Okay, so I'm going to talk about three approaches. I'm going to talk a little bit about quantum consciousness and some of the good things and some of the not so good things there. I'm going to talk about IIT, Integrated Information Theory, and talk about some of the good things and some of the not so good things there. And I'm also going to talk about very large-scale dynamical system simulations, which, I've been involved with, and so I can certainly tell you there are good things and certainly not so good things about that approach. They do kind of different things, and yet they're aiming at different sort of questions. Conscious phenomena, internal subjective phenomena that hopefully we're all experiencing, and the how, what, and why of those phenomena. How do they occur? What are they? And why would we have such things? What's the advantage? What's the advantage to us as individuals during a lifetime? How do they change? What's the advantage evolutionarily to organisms? And that's a kind of key question to bear in mind, because we ought to think ourselves as how will the human brain evolve? If there's an evolutionary advantage to consciousness, then clearly it ought to evolve so it become even more conscious, if that's possible. Okay, so quantum consciousness is somewhere, somehow, there are quantum effects taking place, and those give rise to conscious experience, internal conscious sensations, and so on. And there are well-known objections to this, and I don't propose to go over them. This talk's set out in a paper called Wishful Thinking About Consciousness, which you can find on probably on ResearchGate, but it'll eventually appear in something like the Journal of Complex Networks, because I'm trying to use this as a way of getting people who do complex networks to think more realistically about these sorts of things. But there's something there for everybody. And okay, so quantum consciousness might say that the classical methods are failing. By classical methods, I mean dynamical systems, I mean large-scale, super large-scale network theory, I might mean the reverse engineering of all that, I might mean parallel ideas from AI that we've heard there. But I mean, ultimately, QC, quantum consciousness, kind of has to say, well, that will fail because it doesn't contain a quantum element, and that's essential. So of course, good evidence for quantum is that, we haven't got very far with classical modelling. And we'll see why that is in a minute, and we'll see what's happening about it. That was certainly true up to, say, 5 years ago. Quantum ideas themselves remain speculative, and so there are some challenges there. And I think there's some honest work to do. We're going to hear some about this in some of the talks at this conference. There's some honest work to do in order to remove it from a sort of belief or a cult that this is the way it must go, and start to say, well, the implications of this approach is X, Y, and Z, and make some testable hypotheses. You know, that's what science is. You know, we look at these models and see if they make testable hypotheses and about some consequences, which either can be verified or not. It's not a theory unless it's falsifiable, is it? But actually, it needs to support some predictions. And I actually think that task, modelling with quantum, is much more interesting than a long 30-year debate about where this is all taking place and how it happens. The nature and consequences of quantum consciousness is much more important. There's a similar debate going on in other areas of biology. So there's a thing called quantum biology, which has been subject to various reviews into recent years, and they usually mention consciousness as one of their examples. But each time they focus on examples such as how do homing pigeons navigate, that kind of thing. That's another example. And they need to show how quantum effects are present and how they can control biological and physiological systems. That's the requirement there. I think that's much more important work to do than maybe just arguing about how they come about. In other words, to jump a little bit and say, okay, let's buy this. Where does it take us? And intellectually, that gets us out of a camp of he said, she said, kind of where's it all going on? Which ultimately, isn't getting us resolved. Integrated information theory, IIT. I've changed my mind about IIT over the last few years coming to these conferences, and actually I really enjoy its top-down approach. Let me give you sort of an analogy. We've all heard of an IQ test. We believe that somehow we could measure our intelligence, and there are certain ways of doing it, which we could argue about. These different puzzles that you get shown, and you eventually get a score. And if you're above 100, well done you. If you're beneath 100, go and do the test again. But everybody kind of accepts that different people have different levels of intelligence, and there ought to be some sort of measure for it that obviously it's going to be a bit selective and probably culturally based and all sorts of things wrong with it. But nevertheless, there can be a number. And it would be good in general if the nation could have, some chemical put in its water, tap water, and we'd all become a few points brighter, because GDP correlates to the average intelligence of the nation, right? Of course, there are lots of confounding variables in that, such as health, diet, and things. No, don't worry about it. If we could make the whole nation more intelligent, so why don't we invest in schools? Why don't we invest in schools a bit more, in particular in the ceilings of schools would be good this week. Okay. Look, I like this idea that there can be a number called phi, which is measuring integrated information. And I'll tell you why I like it. One is it doesn't seem unreasonable that some of us would be more conscious than others. It also doesn't seem unreasonable that from birth to death, our consciousness might change as a result of experience, as a result of activity, a result of exposure, as a result of drinking large bottles of red wine too often, that we could, change our consciousness. And we might, through custom and practice, become, super conscious in certain states. And it also implies to me that consciousness isn't a one-way street, which I've long thought. You're not binary, it's not conscious or unconscious, but you don't just get more conscious and then keep what you have. I think that, you know, you could go backwards as well as forwards. And of course, you know, having a single number phi, it's a bit one-dimensional, isn't it? And, you know, it kind of rules out obvious hysteresis effects, you know, and things like that. And but anyway, there it is. So as a top-down concept, this is a really good idea. We can imagine we've got some sort of cognitive machine in a kilogram and a half of wetware, and that beyond cognition, this also does other things, enables other things, some sort of conscious platform, and that we could somehow measure that. Now, unfortunately, the actual calculation of big phi, you know, is a bit of a red herring. Red herring is a false trail, right? Because we have to go through all sorts of contortions and mathematical contortions, and somewhere something needs to be optimized, kind of thing. And it's not quite clear how or where or who is doing the optimizing in this development. But I like it because if there was an evolutionary advantage to being conscious, if there was an evolutionary advantage, then obviously we'd probably be more conscious than the human beings that lived 10,000 years ago. And we might get more conscious in the future. So it's a pity that it's so difficult to calculate phi, because then we could sort of make speculative things. Say, well, you know, what will happen in the future? How could we, you know, mutate the genome so that the human brain developed differently and gave an evolutionary advantage to individuals that were even more conscious? They'd get better partners, they'd have better lives, and they'd eat better, and they'd have more children. That would be a good thing. If the evolutionary forces were somehow driven by an evolutionary advantage that pertained to people with a higher degree of phi. If there is any advantage, it might as well be phi for the point of argument, because that gives us something to optimize. And this is an attractive, very attractive idea. In fact, the idea is so attractive to me, I don't really care how you calculate phi, really, because there's a whole can of worms there. And actually, what I want to do is I want to calculate phi for the networks and systems that we observe physiologically when we're coupling up 10 billion neurons. And of course, another problem there, isn't there? It's a bit difficult to measure phi objectively. I mean, it's difficult to measure your IQ objectively. So, you know, it's going to be difficult to measure phi. But nevertheless, if we could find some physiological observable that we felt was somehow related to phi, that would be brilliant. Okay, little problem is that phi, let's suppose it exists. Let's suppose it's there, and let's suppose it's valid in all of those things. It might be necessary, but not sufficient. Who said that high phi meant that we were definitely highly conscious? Might be necessary, but not sufficient. Are there other things that need to be in place? Right? So worry about that a little bit, but, you know, maybe a high IQ score is necessary for you to be intelligent, but not sufficient. If you haven't had your Weetabix, it's not going to work. So I think there's work to do there, and we'll come back to that in a minute. Okay. Let me just say a little bit about very large-scale dynamical system simulation. So the idea is unlike the phi idea, which would say there is a phi, let's try and produce a plausible way of calculating it and and hopefully apply it to some systems. This goes the other way. We start with what we see, which is a directed network of dynamical objects. Each object is excitable and refractory, and we have a directed network of all of those connections, 10 billion connections, and it's not a random network. It's not even a layered network like we heard about in deep learning or something. It's actually a network of networks. And this is useful for many reasons. So it's got very, very tight networks, which are called neural columns, and they're loosely connected between one another. So there's an outer sparse network of inner dense networks of networks. Mathematics of networks people love networks of networks. They absolutely love it. There's a whole business in trying to take any old network and carve up the modules, the inner dense bits, and it's like community detection and stuff like that. Love it, love it. They don't tend to do it for dynamical systems on networks. They tend to sort of do it for sort of static networks. And there's some work on evolving networks too, which is sort of kind of quite interesting given the sort of neurogenesis problems that we're going to face down the line. But anyway, here's what I wanted to do. I wanted to take 10 billion neurons in a plausible network that looked like that of the human cortex. The connections would all have time delays, due to the tortuosity of the axon synapse dendrite type of connections. And then neurons themselves will be excitable and refractory. You give it a kick and off it goes. 10 billion things spiking away. Trouble is, to do that, you need a supercomputer. You've got 10 billion active cells. And what do you produce? You produce 10 billion spike trains. So actually, reverse engineering, analysing it, is a heavy lifting, right? So we started to think about ways of doing that. And then we could have a peep inside. You can't peep inside a human brain because we can't get down to individual neurons. We could peep inside a synthetic one. What did we see? Well, broadly, we saw that it doesn't matter how you stimulate it. You could stimulate it lots of different ways in different experiments. Broadly, internally, it gets into one of a smallish number. When I say smallish, small compared to 10 billion. Of dynamical modes. The modes exist in time and across the brain, and they're actually quite good candidates for qualia and feelings. The experience of being in one of those dynamic modes could be the experience of the blueness of blue, love, embarrassment. Could all be there, couldn't it? Those are good candidates, and the philosophers don't talk about them because they don't come to conferences like this. They don't know they're there. What's wrong with this? Well, one of the things that's wrong with it is that you kind of, have to make so many simulations, and each simulation is big, and so everything's heavy lifting. But it does make predictions. So one of the simplest predictions made, first of all, we could cut out a single neural column. They only contain 10,000 neurons, and isolate it, and then kickstart it and say, what work does it do? And when you do that, you find that dynamically it behaves like a high-dimensional winding map over a torus. So one-dimensional clock's just got one phase. For your direction, it goes that way, clockwise. A two-dimensional clock is like a winding map over the surface of a torus. It's got two phases at any one time. And then a three-dimensional clock can't draw that. And off we go to 10, 12, 14 dimensions. And we always find that when we analyse the dynamics of these free-running neural columns, they behave like clocks. And there's two ways to do that. One is a sort of discrete Fourier transform, and the other one is sort of singular systems, state space embedding type theory. And they sort of agree, really. So that's quite a good result. Actually, this also implies that since the human brain is limited for energy and volume, even at Oxford, heads can't be that big. Because we're limited by volume in the human brain, then the best way to get the most degrees of freedom would be to have lots and lots of similar neural columns. You don't want the odd neural column that's really big and others that are really small. That would be a waste of energy and space. Right? And of course, physiologically, that's what we see. We know that's what we see. So actually, without any appeal to physiology and dissection, actually we can predict things about the human brain which turn out to be true. It also has another effect. So remember, the problem was we were using a supercomputer, and the one I used was Spinnaker, which was developed with some money from the Research Council of the UK and some money from the Human Brain Project in Europe. And those big brain projects had their own problems for all sorts of reasons that we don't want to get into. But actually, one of the things we thought was, why don't we just replace all the neural columns with abstracted 10-dimensional clocks, and then couple those up? We need 1 million of them, and you can more or less run it on a laptop at that point. And when you peep inside and reverse engineer the results from that, you find the same things you saw in the full simulation. So there is actually a way forward. See, we've all managed this, we've all managed this. People from Whitney down the road have managed it, haven't they, Jonathan? Yeah, yeah, we've all managed this. And what we're seeing there is that the cost of putting this onto a digital platform is really high. But actually, if you abstract a bit, you can then use what's a generalized Kuromoto model, really, where instead of having one-dimensional clocks all coupled up, you've got 10-dimensional clocks all coupled up or something like that. And you see the same things. You see that the dynamical response, internal dynamical response, is dominated by a number of modes, which are good candidates for feelings and qualia. And the tantalizing thing is that if you're in a mode and then you receive some new stimulation, then the mode preconditions the brain's response to that simulation. So the cognitive task of interpreting incoming information, deciding what's going on, conditions the conscious response, and the conscious response conditions the future cognitive response. So if that's true, cognition and consciousness would be entwined. And actually, if you have one, you have the other. No chance of philosophical zombies then. Okay, how do these things all fit together? This is what was really bugging me. So I've written a little bit about this, and it goes roughly like this. VLS, very large-scale dynamical system simulation, is sort of bottom-up and reverse engineering, whereas IIT proceeds top-down in the other way. There is a phi, some questions about that. And but they actually share a lot of vocabulary. Like when we have networks, when we have any sort of system of elements which are pushing each other in a conditional way, then actually the concept of irreducibility is key. This is strong connectivity, that there are many directed circuits and things like that. If it wasn't irreducible, then we could split it up into a master-slave part. And there are evolutionary questions for IIT, so it doesn't seem to say anything about because we can't do it for detailed systems, we can't really say anything about how we might redesign the human brain, even continuously perturb it so that we get more conscious people. That would be brilliant if we could do that. Similarly, within a single lifetime, as we start to develop many more connections from infancy through to adulthood, we go through that period where there are many, many new feelings, many, many new conscious experiences. What's actually happening there to any kind of measure of IIT, any phi? I think also there's an evolutionary question for quantum too, which is what's going there, in particular, how quantum collapse might help. And I'd rather we focused on those questions rather than focused on the where and when kind of questions, because that's part of the bigger argument over quantum biology. And there are many stakeholders there whose minds are very closed to one route or the other, just saying. So next steps. Well, really, quantum consciousness says, well, the classical thing can't work because it doesn't contain a quantum element to it. I suppose the classical thing, the dynamical systems and networks, says that quantum is not necessary, that we've got what we need in there. Actually, we've set ourselves a pretty low bar, haven't we? So there are many conscious phenomena to be looked at, and we haven't really started yet. IIT needs to get much more specific to what I would call realistic cortex-like systems. And it would be really important if we could then show there are some physiological markers, because then you might be able to do some tests and show some sufficiency for high phi being sufficient for consciousness rather than merely necessary. And I think that's a big net. It's far more important to me than inventing other ways to do it. And lastly, for the dynamical systems approach, actually further work in developing and reverse engineering the network of neurons, the network of networks, would be great. But the really big questions there is what do we find out there that would be useful for next generation AI? We already know that elements like attention are very useful in forming next generation of discriminative and generative forms of AI. And equally, there's another problem there of trying to inform next generation chips for next generation computation that may not be binary, that might be much, much different, but might be very good at the sorts of things the human brain can do, make decisions with common sense and gut feel, rather than being data hungry and opaque as deep learning is. So there's a lot of this for everybody, but I think we have to be, you know, really open and honest about which targets, which goals we're setting ourselves, and where we're going with this. Thank you very much, everybody.